So anyway, let's recapture a little bit what we looked at last week. Essentially the total mass balance. And let us just try to remember what this means. M is the total mass in the system. And on the left side we have the time derivative. dm dt is the time derivative of the total mass in the system. And that equals the influent mass flow. So the dot on top of the m means mass flow. In general, the dot on top of an extensive variable means flow. So influent mass flow minus effluent mass flow. So what comes in minus what flows out. And then perhaps you remember that there were some conditions here. For one thing, when we talk about total mass balance, we are not considering, for example, nuclear reactions. So there is no production of mass from energy. And also remember that this is only valid if these mass flow rates are continuous. If there are some discontinuity or something, we cannot really do it, and then we have to write it in the integral form. And when I say the integral form, what I mean is this form here. This is always valid. Of course, neglecting nuclear reactions and so on. But this is valid even for discontinuous inputs. Okay, let's see. There it is. So we used this, and then we looked at a couple of examples. We looked at flow of water, or not water, liquid, in more general. Flow of liquid into a tank and how it flows out. And we saw both a case of a tank with constant surface area. But we also looked at a case with a case of a tank with a varying surface area. And we saw that in those cases we have to do things slightly differently. With a constant surface, we have typically that the volume is equal to density multiplied by level. But in the varying surface area case, we cannot do that. In that case, we get a general function. Volume as a general function of the level. So it's a little bit more complicated. Okay, and then in the end I ran out of time, so we didn't have time to look at using the total mass balance for looking at pressures in a tank. So let's do that as a kind of a starter, and maybe also I will ask you to do that. Well, I'll just sketch the start of it, and then you can continue, and then I will sort of walk around and see that you're working, sort of. so you had better wake up. Example. So one thing I forgot to say is also that, of course, remember to use correct units here. Remember that units that are equated needs to, well, terms that are equated needs to have the same units. So the unit of this one must be the same as the unit of this one. Or, yeah, and also when you sum or subtract the terms, they also need to have the same unit. So these must have the same units. If not, something bad is going to happen with your model. So I think I started to sketch it. And I don't remember exactly how I did it last week, so let's just start from scratch. One of the symbols I use in this course is this impeller symbol. Looks like a bow tie, I guess, but it's an impeller. And what's the meaning of that? It means that the content is perfectly mixed. Okay? So that means that the content is homogeneous. In other words, the intensive variables are the same everywhere. Maybe I should write that. Impeller. Let me write it here, because it's not part of the example. This is quite general. Impeller symbol. So the same intensive variable everywhere. What does that mean? Well, it means that the temperature is the same everywhere. The pressure is the same everywhere. If there is a concentration, that's the same everywhere. The density is the same everywhere. So impeller has a lot of important simplifying properties. So when we assume perfect mixture, everything becomes simpler. So let's say in this case we have a pressure P, we have a temperature T, maybe we have a density, and so on. And then we have a mass flow into the system, and we have a mass flow out of the system. And then we need some expression for these mass flows. There are various ways to do that. I seem to recall, I have a vague recollection that I did something like that. So that the mass flow is equal to some constant multiplied by a pressure difference over the valves divided by some scaling pressure. Did I do that? I think I stopped somewhere around there. There is an alternative way of doing it, and we'll come back to that, but let's use this for now, and then I will just get some more space. So let's use this. And the starting point, what is the starting point? What's the first thing we do? Mass balance. I recommend that you use this procedure because it's easier to avoid mistakes. So be very systematic when you formulate models. And the first thing you do is to set up a balance law, and in this case the mass balance. So I just want you to, in your exam papers and so on, just write down the general mass balance. Because you are going to use it. And then the second step is to try to figure out what we mean by these various terms. I haven't said yet what's the purpose of this model, so maybe I should state that. It's good to know where we're going before we start to go. Find how pressure P varies with. So find out how the pressure in the tank P varies when the mass flow into the system changes. Well, okay, that's maybe not a very, well, let's change it. Let's say when the inlet with PI, let's say that we specify an inlet pressure. So then I have to scratch down the blackboard again and just add here PA and then PI is the inlet pressure, and PA is the ambient or pressure. So we are assuming that we press something into the tank and then it flows out. So find how the pressure P varies with the inlet pressure PI. So the second thing we need to do after, first we state the mass balance, and secondly we try to relate the terms in the mass balance with what we are interested in. Okay? Relate terms in balance law with what we are interested in. Okay? So, mass. How can we relate mass to pressure? Then, of course, some of you know it already. Maybe if you're a PT or ET student or something, and some of you maybe have forgotten some things. If you're systems, well, IIA, is it IIA now? It used to be Systems and Control Engineering. It's Industrial IT and Automation, I guess, is it? I have to learn the new name. And then also Electrical Power Engineering students. So you have to remember the ideal gas law. So let's assume ideal gas. Pressure multiplied by volume equals number of moles multiplied by gas constant multiplied by absolute temperature. Okay, how is that related to mass? M. And the number of moles is directly proportional to the mass. So we have mass equals number of moles multiplied by molar mass. Okay? Next, we also need to relate the flow rates to what we have, what the information we have. So we have mass flow in equals to some valve constant Ki. Here I am sort of suggesting that this one is general for any valve, and then for a particular valve I need to add an index to say which one I'm referring to. So we are sort of assuming that the valves can be different, and of course there will be different pressure drops over the valves. Delta P is the pressure drop. So what is the pressure drop at the inlet? Pi minus P. And then similarly we have at the flow out, effluent, and we use the same scaling pressure in both cases, so it's a constant. And remember that since we have a perfect mixing, the pressure is the same everywhere. So the pressure is the same here and here inside of the tank. So we use P in both cases. If the pressure varies in the tank, we need to use different pressures, but we have to pretend it's the same, just for simplification. So what else do we need now? Let's try to summarize the model so far and then see what is missing. Okay. That's the first we wrote. Then next we have PV equals nRT. We have M equals N times molar mass. We have And then finally, so this is the model so far, just summarizing what we wrote on the previous board. 1, 2, 3, 4, 5, 6, 7 equations. And then we need to start to count the unknowns. We have 7 equations. How many unknowns do we have? Mass, that's 1. Influent mass flow is 2. Effluent mass flow is 3. Pressure is 4. Volume, well, that's a parameter, a constant, so we need to know that one, so I don't count that. N, number of moles, 5. R is a constant, so we don't count that. Temperature, what about that? Well, we don't really, we could say that it's a variable, but so let's include it. So we have 6 then, 6 unknowns. And then mass, I've already counted. N, I've already counted. This one I've already counted. Or no, that's a constant, so we don't count that one. I've counted this one already. This one is a constant. This one is unknown. So we're 7. This is constant. This one is counted already. This one has to be constant. 8. Right? And then, let's see here, this we've counted. 9 perhaps. Okay. And this one, so we have 7 equations and 9, was it 9 unknowns? So that means we have a problem. So we have to have two more equations, kind of. Did you understand what I was doing? Okay, so we need 2 more equations. And one equation, so 7 equations plus and 9 unknowns. So we need more. So what should we do? Well, for one thing, we say that pi is an input variable, so we know that one. Pi is a known input variable. So that's known. So then we have reduced it to, well, either we have reduced the number of unknowns or we have added an equation anyway. So now we only have one problem, one missing. And as some of you suggested, and I think I mentioned that last week also, that we will pretend that the temperature is constant. Okay? Pretend that the temperature is known. Is that realistic? Not really. So there are 2 ways to handle it. One is that we are going to do in, I guess, 2 or 3 weeks. Introduce energy balance, and the energy balance will give the additional equation for the temperature. Or alternatively, well, that gives dynamics of the temperature. There is an alternative way. assuming anyone? Adiabatic expansion. Then we suggest a specific relationship between the pressure and the temperature, which is quite common. So that's, but energy balance is the best way to do it. So we have now a complete model, and observe that it's in the standard form, standard DAE. Which we can write like this. We have the differential equation, and this is not an ordinary differential equation because it depends on more than x. It also it depends on some algebraic equations, variables set. So we need an algebra set or a number of algebraic equations here to complete the model. And then we also have the output, which essentially is what we ask, what we are interested in finding. So in this case, it's the pressure. The input is kind of the input pressure. Could be also other things, but let's assume that. So let's see how this general standard differential algebraic equation relates to this model here. What is x, what is z, what is u, what is theta, what is y? So x is the differential variables, the ones that we differentiate with respect to time. And what is that in the model? It's the mass. The algebraic variables is a little bit tricky maybe, so let's wait a little bit with that. So we take the inputs first. Inputs is kind of very easy in this case. It's pi. And then we have parameters. Parameters are constants. What are constants in this model? We can start from, let's be systematic, volume, gas constant. We have said that the temperature is constant. That's not really true, but we pretend that just to be able to simulate this or to formulate the model now. Molar mass. Valve constants. And let's take them together. And then scaling pressure. Okay. PA, ambient pressure. Ambient pressure could alternatively also be an input. If the ambient pressure varies, it's an input. But if it's constant, like typically atmospheric pressure is, well, normally relatively constant. Of course, you know the pressure varies. We talk about high pressure and low pressure. And when it's high pressure, normally the weather is nice, and during low pressure, the weather is bad, typically. So you know it varies. But let's pretend it's not significant in this case. That seems to be all. The output is the pressure, what we're interested in. So what did I say about algebraic variables? It's essentially, if we forget the output, it's essentially the all remaining quantities. So if we start, we see that it's m is okay, m dot I, m dot E, P. Remember that P can also be part of the output. So, okay, what else? P, N. R and T are constants. Okay. Delta Pi. Delta PE. That's it, I guess. Is it? Tell me if I missed one, but it looks like that's. What?
N is algebra. I mean, it's Z included. Z included N as well. I mean, it's algebra variable.
Yeah. This is an algebraic equation. So it's an algebraic variable. Yes.
But we thought it's supposed to be a parameter, no? Like number of moles.
No. N is not here.
Okay.
N varies because the mass varies.
Okay.
But it's capital M. Capital M is the molar mass. That is constant, but not the mass. So capital M, the molar mass, is constant. For air, it's typically 29 grams per mole. For oxygen, and what is 16 or? 32 for the molecule. So the molar mass is 32 for oxygen. And for nitrogen, it's 28. Yeah. Carbon is 12, so 24, I guess. Well, whatever. I'm not a chemist. Yes. What about pressure? P. I've mentioned it here.
That is output variable and algebraic variable also.
What?
That is output as well as.
Yes, I said. Forget the output when you say the rest. Yeah. Algebraic variables can also be in the outputs. So when I say take the rest, it's essentially not the rest after you set up x, u, and theta. Okay? So the algebraic variables can double in the outputs. Also, the state or the differential variable can also be in the output, and also the inputs and so on. Okay? So this is a DAE. You can solve it using Open Modelica, for example. And you just write the equations as I've written them here, more or less. Has anyone tried Open Modelica? Yeah? Anyone else? With success or without success? Okay? You should try it. I recommend it. For one thing, you learn much more when you sit and try to do it yourself. You can essentially just copy what I've done, just copy and paste from the PDF file if you want to. And it should run unless you do something, or unless you didn't succeed in installing tools. I have used, let's see, there is a video about how to install an ASCII editor called Atom. It also illustrates how you can download and install or install a Modelica plugin, so you get syntax highlighting. When I first, a colleague of mine told me about Atom, I liked it at first, and then I stopped liking it, so I don't use it anymore. And the reason I don't like it is I don't know. I shouldn't say that the developers are stupid, but for some reason they have decided it's not possible to print the file, which to me is completely, I mean, if I debug things, I have to print it and use it with a pen. If you don't need to do that, if you like to sit and debug on a computer screen, then it's fine. But unfortunately, the only way to print from Atom is to install another HTML plugin and then export it to HTML and then print it, which to me is kind of clumsy. There is another possibility, Notepad++. I'm working on writing the description to do that in my updated lecture notes that will hopefully come out in not too many weeks. And I also have a file for downloading that. I have tried in the past to put this sort of plugin. Well, Notepad++ is a general editor. It's free, of course. There is a plugin that you can use to get syntax highlighting in Modelica. I have tried in the past to include that in Fronter. It's without very much success because the plugin is an XML file, I think. And the problem when you open that from Fronter, it opens in a web browser, which is not what you're supposed to do. So I will try to make it downloadable from Dropbox or OneDrive or something. And then you can simply just download it and place it in your computer, if you have Windows operating system. I don't know how to do it in other. I'm sure it works also on Macs and so on. You can write it in any ASCII editor. You can use Notepad or whatever you have. You don't have to use Notepad++ or anything. The only difficulty is that then you don't get syntax highlighting, but it should still work. Okay, so I recommend you try it. Installing OpenModelica is very simple. You just go to openmodelica.org and download it on the computer you have. Okay? So I recommend that you do it. So if you do that, you can write the model more or less as it is here. So maybe I should indicate how you do it. You write a file that says model. For example, you give it a name. Let's say pressure tank or something. Like that. The model statement just says that you create a class in Modelica. So this is and then in Modelica you need to end this class with the statement that's called end, and then the name of the class. And then semicolon. So this has to be the first line, and this the last line. You can call it whatever you want. You can call it my tank or whatever. And standard, that's one of the things I need to upgrade from in the lecture notes. The standard in Modelica, I didn't know that when I started, but the standard is that class names should start with a capital letter. So anyway, then you need to define parameters. And you need to say what type of number it is. So parameter says it's a constant, real says it's a real parameter, and then you have to, let's see, then we just take the values we have here, v, let's say 10, and then every line has to end with a semicolon. Okay, and then you continue parameter real, what's the next one? It's R, 8.31. Make sure that you use consistent units. If you want to, you can add a comment, but that's up to you. You don't have to, but you could, and you put that in as a string, gas constant, for example. That's voluntary. You can add a text that describes what it is, and it's recommended to do that. It's also recommended to include the unit in this string, just to make sure that you document what you're doing. And so on, all the way to parameter real, what's the last one? PA. And the syntax in Modelica is similar to in MATLAB and Python, I guess. 1.01 E5. That means 1.01 multiplied by 10 to the 5th. Okay? And then you need this. So we start. You don't have to do this first, but I like to start with the parameters first. Then you need to define the variables. So let's start with the algebraic variables. So then they are not parameters, so we should not start with real. We should not start with parameter, we start with real to say that it's, and then it's automatically assumed that it's a variable. And then the name, let's see, m. So we have to invent some notation for m dot I, so I use mdi. md for dot, mass dot I. And then, of course, you cannot give a value because it's supposed to find that value. Etc. And then all the way down to this one. And then we also need to specify the differential variable. Real m. And for that one, we need to specify a start value. We can specify start values in, see, what is it? Start equal 1, for example. And if we want to, we can also add, I think, fixed equal true. That gives the initial value. If you remember from last week, we also said that we need to specify the initial value of a state. So start means that it's the initial value and it's the value we, for example, 1 kilogram or whatever. Fixed equal true, what does that mean? Well, we can give several initial values. We could also add the initial value for the pressure, for the number of moles, and so on. But then the solver has a problem because you have specified too many initial values, and then it has to figure out which one is the right one, or maybe take some least squares choice. If you say that fixed equal true, then it has to use this value. And if you use fixed equal true for several variables, the system will crash. So fixed equal true is a way to say which one is it has to start with this initial value. And then, okay, and then you also need to define the equations. And then you have a clause or something, a statement that says equation. After you have defined all the parameters and variables and so on, you have defined the equations. And I'm sort of running out of time and space. So let's get back to the equations after the break. Let's continue. I'm running a little bit out of space down here, and well, let's see. Of course, I don't have space to write all the equations, but let me indicate it. So we can write, for example, the differential equation. That would be der parenthesis m and parenthesis equals mdi minus mde semicolon. And here you observe that Modelica supports an operator or a function der, which means time derivative. So this means the time derivative of m equals mdi minus mde. And then p v equals nRT. Etc. And then end, what did I call it? Pressure tank, was it? Yeah. So from this kind of sketch of the equation section, observe that Modelica has support for an operator or a function that means time derivative. Okay? Also notice that in Modelica is a language that is so-called equation based. So that means that equality means equality. It means equation. And of course, in an equation, you can have terms on the left side and terms on the right side. So this is perfectly legal in Modelica. And when you run Open Modelica, it will sort your equations. And then without you knowing it or without you noticing it, it will move things to the right side and convert equality to what is known in computer science as assignments. That is used, for example, in C and MATLAB and Python and so on. In C, MATLAB, and Python and so on, equality does not, or this symbol does not mean equality. It means assignment. It has a different meaning. But in Modelica, it means equation. So, but when you're running Open Modelica, it will, without you don't have to do anything. It will automatically convert the code to C and then compile it and run it. And in that process of converting it, it will rearrange equations, change the order, move things to the left side, and so on. So this means that if you want to formulate a model in dynamic model and then use Open Modelica, you don't really have to change the model very much. You can more or less code it the way you write it. Okay? So this works because Modelica supports differential algebraic equations and is equation oriented or equation based. So let's. I had a couple of questions in the break, and let me comment on if I remember them. One was that in the notes I use ambient pressure here. Well, maybe. I don't remember exactly. I didn't reread my lecture notes, so I just invent the examples. So maybe they're different from what you find in the lecture notes. But to set the scaling pressure equal to ambient pressure is probably a good idea, because then you get the value inside here to be somewhere between 0 and 1. So if you want to choose this scaling pressure, and I have to do it somewhere here, I would probably say that parameter real PS equals PA. Okay? That was one comment or question. Another question was, what is the difference between DAE and ODE? So what's the difference between differential algebraic equation and ordinary differential equation? So let's find out, or you will find out. So now you have to work. So observe that this is a standard DAE. dx dt equals function of x, z, u, and theta. Okay? And then we have an algebraic equation, and we have output equation. When we have ODE, we need to eliminate the algebraic equations. We cannot have algebraic equations. So that's what you're going to do now. And I will just remove some from the text from the blackboard so that to clarify what I want you to do. A generic or general DAE has this form. Notice the difference. In the ODE there is no set, which I use for symbol for algebraic variable. Okay? There are a couple of things more to notice. One is that the f here obviously is not the same f as here. So it's a different function. Also, the function h here is obviously different from the one here. One reason why I can say obvious is that here there is a set variable, but that's not here, so they have to be different. Also, there is no g function, there is no algebraic function. And one more thing is important, and that is, what about the quantities? The x, well, I said that z is out, sort of. What about x, u, theta, and y? Are they the same in the two cases? Not necessarily. But, well, there are some things that have to be the same. Input-output relation or input-output quantities have to be the same. So what affects the system and what you get out of it has to be the same in both cases. So that means same u and y as in DAE. Okay? Everything else can be different, including the state x. So now I want, this is a task for you to do right now. Try to start with this DAE and convert it into an ODE. You have several choices you have to make. For example, you can choose the state or, well, the differential variable x. One possibility is to let it be m. Another possibility is to let it be the pressure P. It could also be the number of moles. You have dozens of possibilities. Well, not dozens, but a few. So you could probably even let it be m.I or something, I don't know. That would be a kind of weird choice, but most people would probably use the pressure. And the reason is that you're really interested in the output. And if you choose the pressure, you get the output directly when you solve the equation. So try to find the ODE form. And you should need about 5 minutes. In an exam, I would probably give you 5 minutes for that. For this simple model. For more complicated, you would get more. Just to give you a hint, it's very easy. You just start to insert the expression for m into the differential equation, and then the expression for n. You have to solve the ideal gas law with respect to n and insert that, and so on. And then take advantage of differentiation of constants. Kind of, you can take that out, and so on. It's probably this one. Okay, go ahead. Okay, so let's see what we have. So let's try to expand on this expression. Like this, and then we have n. We have to solve ideal gas law with respect to n. So we get like this. And now we have, of course, assumed that volume is constant. Well, it is. We have gas constant is constant, but we have assumed that the temperature also is constant. So we get like this. And next we do the same for the right side with m.I and m.D. And then finally we can solve it with respect to the dp dt. So we need to divide by this on both sides. So we get like this. This is an ODE. Why is it an ODE? ODE means ordinary differential equation. It's an ODE because we can write it in this form here, where the inputs and outputs are the same as in the other model. So it's kind of multimedia presentation with music.
Why do you divide on RT?
I divide with this.
Under in mass flow reference when you have inserted everything in the last equation.
That's because it's a typo. That's of course correct. So I occasionally do things like that, so please. Could it be the Whistler who sort of disturbed my train of thought, or maybe he hadn't started when I wrote it? So, why is this an ODE? Because we can write it in this form. We have the P is now the state, X. So X is P in this model. Inputs and outputs are the same as over there, so they should be Pi and P. There is no algebraic variable Z, so the rest should be parameters. And we can check it. Parameter, 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 input, parameter, 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 parameter. So it is in this form. And because of that, we can solve it using Python easily, for example. This one can normally not be solved in Python and MATLAB. But this one can. So you see that even in this very simple example, we had to do some manipulation to change it from DAE to ODE. And in this newer version of the course, I have decided that since we have DAE solvers like Modelica, Open Modelica, let's put less emphasis on this manipulation and more emphasis on formulating the models. So because of that, I will emphasize developing DAE models. But of course, you also have to know or understand how to change it to ODEs in case you want to simulate it using Python, for example. Well, final comment, you don't really have to go this far to write it in Python. It's, I guess it's sufficient to do this step. You don't really have to do all this. In Python, you could, for example, do the following. And I'm not going to write Python code, but I'm just going to indicate the sequence of expressions. So let's see what we have. We have like this. like that. What else? Yeah, and then finally multiplied by so you could do it in this sequence in Python or MATLAB. Where the last step is that you define the sort of so-called vector field of the differential equation. So you don't really have to insert this into this, but you have to make sure that you define quantities in the correct order. So you have to define delta pi before you use it here, and you have to define m dot I before you use it here. So in assignment-based languages such as Python and MATLAB and so on, you have to define quantities before you use them. In Modelica, the order of equation is immaterial. You can choose whatever order you want because the equations are sorted. Okay? And also you can have expressions on both the left and right side of the equalities. In Python, this symbol does not mean equality, but it means assignment. Essentially, it means that this expression is assigned to that symbol. And then this expression here is assigned to that symbol, and so on. Okay? So, I don't know if this made it clear what is the difference between OD and DAE. Hopefully you understand it. We will see more examples of it. In some of the analysis part, we have to actually, or at least I will use ODE formulation to, for example, when we discuss stability and so on, because it's more developed. Okay, so let's say 15 minutes before break. So we should start on the topic of today. We have sort of started already, I guess, in a way, because we are going to use, or mole balance is going to be important and we have sort of indicated that already. So let's. I guess I should clean this one. So the next topic is species balance. We have already looked at the total mass balance. But now we're going to look into balance of species. So, what does the word species mean? You probably know it from biology and Darwin's book on the origin of species. So, like, examples of species are elephant, zebra, cow, whatever. We will use it in a more technical meaning. Just one caution on the word species, and I did mistakes on that in the past, and maybe there's still some remainders, hopefully not too many. Species is a little bit special word in English. It has the same form in singular and plural. So it is one species and two species. Okay? So in the past I did a mistake and wrote species balance for one, but it is correct, it's species balance. So how do we change it, the mass balance when we start to talk about species balance? It's very easy. Let's see. Like that. The mass of species J, we could have a large number of species, but the mass of species J in the system is equal to the mass flow of species J into the system minus the mass flow of species J out from the system plus possible generation of the species. Okay?
Excuse me?
Yes?
Is it m dot j comma I?
Yes. J is the sort of index that indicates what species we're talking about. So, if you talk about your bank account, for example, you could have the accumulation of species or money equals flow of money into the system minus flow of money out of the system plus some generation, which could be interest rate. If we talk about this classroom, we have the total mass of persons in this room. We could sort of count you all and add up the mass. Then we can say, okay, we are now interested in different types of species. One species could be people with glasses, and then people without glasses. So, then we have, let's see, 1, 2, 3, 4. 4 people with glasses here, and 1, 2, 3, 4, 5, 6, 7 there. So then, if one of the persons with glasses go out, for example, then there is this affects this one. What about generation? If you take off your glasses, then we have. Then in some cases they also talk about birth and death. So then there is a death of one person with glasses, and one person without glasses is born. Okay? So you can take them off and on. Okay? You could also have other types of species. We could talk about persons with blonde hair and dark hair, for example. And then we could also have more complicated species, people with glasses and blonde hair, and people with glasses and dark hair, and people without glasses and blonde, and people without glasses. So you could have very complicated types of species. Okay, so there is an example in the lecture notes, what I call the barn dance example, which is kind of stupid. But you can take a look at that. Sort of a non-chemical example of chemical engineering, I guess. Chemical reactions. So, in this course, we will narrow down the meaning of species. And it's what's the, I I don't know what I should call it, item or something, or let's see, species are distinguished by chemical formula example, hydrogen is different from water. They have different chemical formula. Different chemical structure. What does that mean? It means that some particles or some objects could have the same chemical formula but different structure. There is one example in the lecture notes. There is an obvious example is, for example, glucose and fructose. They have the same formula, but they have different structure and different properties. Okay, and the third thing that we will use is different phase. So that means liquid phase or vapor or gas phase or solid phase. So the point is that when we talk about species balance, at least in a kind of a chemical engineering or very relatively simple connection, we set up the species balance. We have to formulate a different species balance for each. If species have different chemical formula, we need different species balance for them. If they have different chemical structure, like glucose or fructose and so on, we need different. They are different species, and we need a separate species balance. And if they have different phase, like water in liquid phase and water in gas phase, then we also need separate species balances. Okay? So that's the idea. Of course, these ideas can be generalized to more complicated systems, and sort of as the barn dance example indicates, we can also use it in more other types of systems. One important thing to notice is that what about the mass of, or the generated mass of species? If I sum it, if we take the very simple example of persons with glasses and persons without glasses, and if you could help me again. No, he took off his glasses. Did the sum of mass of people with glasses and without glasses change? No. So that means that if we sum over all generated mass of all species, the sum is 0. There is no generation. There is no total generation. And if we also define in the obvious way like this, we see that by summing over all species balances, we get back to the total mass balance. Okay? If we sum all these, and we use this fact here, and these obvious definitions, we see that this one leads to that one. So by summing all the species balances, we get back to the total balance. And of course, it must be like that. So suppose we have now 3 species. Normally written like this. So we have a chemical reaction between hydrogen and oxygen, and we produce water. So we have 3 species, hydrogen, oxygen, and water. So to describe this, we should have how many species balances? 3. 1 for hydrogen, 1 for oxygen, and 1 for water. We have an alternative, however. Remember that the total balance is still valid. And the total balance comes from summing the 3 individual species balances. So alternatively, to have a species balance for hydrogen, oxygen, and water, we could have a total balance. But since the total balance is a linear combination of the others, we can only use 2 other ones. So we can use total mass balance and then species balance for hydrogen and oxygen, or hydrogen and water, or oxygen and water. But we cannot use total mass balance plus species balance for all 3, because then we have 4 equations and we really only have 3 independent equations. Okay, so but it's very common to use total mass balance in combination with species balances. And then we use 1 less species balance as there are species. Okay, so let's take a break and 15 minutes, and after the break we will look at an alternative way of measuring the amount of each species, which is, instead of, I've talked about the mass of persons and so on, and in general the mass of species. Instead, we will try to count the number of people or species, and that will naturally lead to the mole balance. So, alternatively to measuring the mass of a species, we could count the number of species. The fundamental difference is that in one case we look at the world as consisting of particles that we can count, and in the other case we have a continuum. So when you talk about the mass of this sponge, we think of it as a kind of a unit, continuously varying in space. But when we talk about, we could alternatively count the number of atoms that constitutes this sponge, and then we talk about particles. So, of course, when we look at people, we can talk about their mass, but we can also count their number. So that's an alternative when we talk about species balances. Let's do it here. So the particle understanding. of the world. We could say that we instead formulate a balance for the number of species of each species, the number of elements in each species. Like this. So we could count the number of people with glasses and the number of people without glasses. Or we could count the number of people with blonde hair and dark hair. Or we could count the number of people which are simultaneously blonde and have glasses and blonde without glasses, and dark-haired with glasses and dark-haired without glasses. And the generation term could be when they take on or off their glasses, or, well, color their hair or whatever. Okay? When we talk about, we could do the same, of course, with atoms and molecules and particles in general. And then, of course, you know that we would have a huge number of oxygen molecules in this room, for example. So it's not really, it's kind of clumsy to operate with the number of chemical species because the numbers are so large. So why not scale the number? So we could instead divide by some scaling number in every term. Like that. That's a possibility. So what could be a good number to scale with? Avogadro's number, for example. Which is something like 6.02 10 to the 23rd, which is a huge number. And if we use that particular scaling number, this scaled number has a name, and that is mole. And I will use the symbol lowercase n. Okay? That's all there is to the mole number. It's a scaled number of particles. And it's scaled with Avogadro's number. And for chemical systems, it's much more convenient than counting the actual number. Of course, in population surveys for countries, for example, where we count the number of people, we could, for example, make a distribution of heights, for example, in the class here. In that case, we don't use moles because the number would be so small. So for other types of, for example, when we are going into like nanotechnology and so on, then maybe the number of particles in the system is so small that maybe in that case we count the number instead of using the mole number. Maybe. Anyway, in most cases in this course we will use the mole number, and then we clearly have a mole balance. Like that. So these are equally valid in some. We could either use the mass-based species balance, or we could use the number or particle number based species balance, or we could use the mole balance. Of course, they're used for slightly different things normally, but in the case of chemical systems, there is an added property of the particles that is important, and that added property is not valid for complex systems like people. And what is this property? Any ideas? It's probably difficult to guess. All species within a group have the same mass. So all hydrogen particles have the same mass. All oxygen particles have the same mass. If I look at you here and say that one species is people with glasses, most likely you have different mass. And that makes it more difficult to convert from particle description to mass description. But for chemical systems where the species typically all have the same mass within a species, then we have for many chemical species, we have this relationship. The mass of the species equals the number of moles of the species multiplied by the molar mass of the species. So if we know that we have oxygen, for example, we assume that all oxygen particles have the same molar mass. If you really go into things, it's not that simple. But according to a friend of mine who's an expert in thermodynamics, he says that water, for example, is not only H2O, it's also polymers of H2O. So you have H2O that is kind of linked with H2O, and you can have a sort of with maybe some polar forces or something, and they're sort of construct chains in a way, and that's maybe the reason why you have, for example, that the coldest, the heaviest water is at 4 centigrades. So that also leads to, when I say for many chemical species, there are many also systems where this is not true. For example, if you have polymers, example of polymers, I guess plastic, some types of glue are polymers, and they consist of long chains or even much more complicated geometries. Could be networks of small molecules that are repeated many times. For example, polyethylene contains, I guess, ethane that is sort of repeated many times, millions of times possibly. And if you have something made of plastic, I don't know what this is made of, but if we could pick out or split it up in all the different molecules, some of them will be enormous, maybe molar mass of millions, and others will be smaller, so there will be a distribution of sizes in this. And in that case, we cannot do this. In that case, we would have to talk about some average mole mass or molar mass. The same is true with in biochemistry, with like microbes and so on. They're also complex species, where we cannot say that each species have the same mass. We cannot do that. So also in that case, we need to, and even more complex for people, animals, and so on, mammals, and so on. So in those cases, we cannot do this. But for very simple species, this is valid. And we are mainly going to work with these types of species. If you have more complex species, for example, like people, if we wanted to talk about the height of people, we could talk about a height distribution, for example. We could talk about hair color. We could talk about a color distribution, and so on. For polymers, it's common to talk about chain length distribution, for example, or mass distribution. Then you get some more accurate description of it. But then, of course, it's much more complicated. So anyway, with under this assumption that the species have the same molar mass, every individual in the species have the same molar mass. Based on this assumption, the mass balance and this particle description is equivalent. And we can go from one to the other. It doesn't matter which one we use. So one of the key things we said here is for when we use mass-based species balance, if we sum the number of masses, sort of generation of mass for all species, that is 0. And then, of course, an interesting thing is, what if we sum the amount in moles of generated over all species? What will this be? Can we say anything about it? Is it 0? Unfortunately, it's not 0 necessarily. It could be 0, but normally not. Why? Well, very simple example. Look at this one, for example. This is a so-called stoichiometric reaction. So if there is a reaction going on between hydrogen and oxygen, we produce water. And if we use this approach, use mass-based species balance, then it adds up to 0. But if we count the number of molecules or particles, or the number of moles, we observe that here we have 3 molecules that react and become 2. So that means that it's just a simple indication that this is not valid when we talk about particle balances or mole balances. So in general, this is not 0. It could be if there is no generation, of course, it could be 0, or it is 0, but in general, it is not. Of course, it's also easy to see it if we look at if we look at it this way. This is true, of course. This simply comes from using this one. We see that if they have the same molar mass, then it will be 0. Because then we can take this 1 divided by mj outside of the sum. But in general, they don't have the same molar mass. Okay, so let's try to use this. Let's not focus too much on this theoretical part, but let's see how we can use this in examples. So let's, of course, also we also need, but I will first do an example. We also need to look at this term here, the generation term, or alternatively this one here. And this is related to chemical reactions. And for some of you, you know a lot about chemical reactions. Probably maybe even more than me, I don't know. I have taken some course in reaction engineering, so I know a little bit, but and then some of you probably just get nightmares out of the just thought of chemical reactions. So I will try to make it simple. It's not necessarily difficult, and you don't have to know a lot of reaction engineering in this course. If you need some reaction rates and so on, I will provide them in exams and so on. But you should understand how they interact with the balance equations. But let's first do a simpler example. Let's, for example, and just to warn you, I'm just inventing an example now, so you will probably not find it in the lecture notes. So let's suppose we have two source tanks, these two, and they perhaps, let's say that they have this one has pressure P inlet or influent 1, and this has P influent 2. Well, this does not mean squared, so well, maybe that was an unfortunate notation. PI1, PI2, they have pressures, PI1 and PI2. And let's say they have temperature TI1, temperature TI2, and pure species A, and here, let's see, A and species B. Okay, so we want to flush this into a tank and mix them. So we have this mixing symbol, that means perfect mixing. And we have a total pressure in this tank of P, we have a temperature of T, and we have so-called partial pressures, PA and PB. And then everything flows out here. And let's see, okay, we have we are going to use mole balance, I guess. So let's see. This is the inflow of A. Here we have the inflow of B, and then we have the flow out here. So it's starting to get tricky, maybe. It's maybe interesting. So there is no chemical reaction for now. So that means that the reaction terms will be 0. So, but we are mixing two species, and in this mixture, or in the mixed tank, we have a total pressure which is the sum of the partial pressure, or partial pressures. So let's find, for example, let's be modest and say we only want to find PA, and how that depends on this. Depends on inlet pressure Pi1, inlet pressure Pi2, inlet temperature Ti1, and inlet temperature Ti2. Assume constant temperature T. And if you have started to read my lecture notes and seen some examples, you may remember that I have used something that in the previous lecture notes you have, I call it functional description, but I've decided to change it to functional diagram. So that's functional diagram. That sort of contains this information in a short form. So. So we have this system. We don't really say anything about what is inside. This is basically defining inputs and outputs. And the model can be of various complexity depending on what assumptions we do. But we can still have the same inputs and outputs. But I have already indicated a very important simplifying assumption, and that is this mixer. What does the mixer say? It says that the pressures and partial pressures and temperatures and so on are the same everywhere in the tank. Okay? That has a consequence. It means that the properties inside, which is the same everywhere here, is also the same at the flow out. Okay? However, at the flow in, there will be a jump, because here you have pure species A coming in, and then it jumps to a new value because of the mixture. So from the inlet, influent, there is a jump. But when it's in the mixture, everything has the same value, and it's also the same value when it flows out. Okay? So let's try to model this, and then let's interact a little bit during this. I don't expect you to do all of this since it's the first example of species balance and mole balance. So, but let's discuss a little bit how to proceed. What is the first thing we should do? What? Write the balance models. Okay? So what are the balance we could... so one, we are going to use mole balance. And observe that I include the generation term, although I have already said that we're not going to use that. But in the first step, I think it's a good idea to set up the general balance law. And then in the step 2, we introduce a statement that we don't have a reaction. So in an exam or in a test, I will not, you have to remember this. I will not give that for you. You have to, that's one of the few things you have to remember. There are, of course, when I say few, I don't really, it's not that few, but this you have to remember. So so we need to relate these expressions to what we're going to use. So first thing we notice is that we say there is no reaction. What does this symbol that I used mean? Have you seen it before? Maybe? Identical to or equivalent to. So it's identically equal to 0. What by that means, what I mean is that it's always 0. It's not just by at some point in time it's 0, but it's always 0 in this case. It's not important. We could have used ordinary equality for that matter. But when I use 3, I kind of emphasize that it's always 0. In this system, because there is no reaction, there is no chance that it could be different from 0. So what else do we need? We need ideal gas law. Okay, this is true there, but we can be more specific than that. Ideal gas law is also valid if we consider species. So this is also valid if we have index J on P and N. So the partial pressure of species J multiplied by the volume is equal to the number of moles of species J multiplied by R multiplied by T. That's also true. So I haven't really said yet, but what are the species? We have two species, A and B. I don't really say what it is. It could be oxygen and nitrogen for that matter, but we don't really have to say what it is in this example. Okay, so this is the ideal gas law, slightly more general than what we saw in the past. What about the total pressure that we have up there? That's simply the sum of partial pressures. Let's see, what else do we need? Okay. Yeah. So then, by using these, we can we have actually expressed Nj, right? That kind of comes from this one. By combining Nj here and this one, we get the partial pressures. And then also we need the total pressure, so that's why I computed this one. We need to have some expression for the flow rates. And there are various ways of doing that. Let's see. One interesting way to do it is to say that we can reuse ideal gas law one more time, because it's also valid in the case of flows. Okay? So it's valid for flows. And then we have to remember this, my rule of thumb for using this dot on top of in flow. That can only be done for extensive variables. So we can say that flow form, kind of ideal gas flow, how is that? If I should turn this into a flow form, what are the extensive variables? Is P an extensive variable? P is intensive. What about V, volume? Intensive, extensive, so we can use a dot on that, so flow. What about N? N is extensive, so we can have dot on that, and then R and T. So this is a flow form of the ideal gas law. Pressure multiplied by volumetric flow rate is equal to molar flow rate multiplied by gas constant multiplied by temperature. So that gives us the molar flow rates here and here. No. Here and here, well, also here. Yeah. So, but we see that, okay, if we take a look at this sort of ideal gas flow law here and compare it to here, we see that we have inlet pressure, so we use that one here. And then we have the volumetric flow rate through here. We don't know that one. Molar flow rate, that's what we want to find. R is okay, and temperature is, we have the temperature here. So we need, in addition, we need some expression for the volumetric flow rate. So what is a possible expression for that? We will use this kind of standard expression that I've used in the past for mass flow, but we will pretend it's valid also in this case. The idea is that there is no flow rate unless there is a pressure difference. If the pressure is the same on both sides of the valve, there is no flow. Okay? So now we are equipped with some general ideas. And since this is a slightly more complicated model, I tend to divide it up into 3 steps instead of 2 that I've used in the past. So the first step is for the general balance equation. The second step is some general ideas about what balances I need. And in the third step, we sort of write them out in full, the entire set of equations. So let's do that. Should we have a break first? 15 minutes, and then I can clear the board and it dries up a little bit so that you can see better. It's recorded. So let's start again. So let's do a third step where we extend on these more general expressions and formulate more the complete model. So if we start with the balance equations, we need one for each species. So we get and as I've said, we sort of skip the generation term. Then we will have a similar one for species B. Like that. And then we have ideal gas for both species. Okay. And we could also say that we will need later on the total pressure. Okay. Then we need the flow rate, the molar flow rates in and out of the system. So if we look at that one, the flow form of the ideal gas law, we see that we have Pi1 multiplied by V that was not my knee, it was the microphone. Pi PI1, the inlet pressure for from the tank containing A. I could, of course, also have call this PIA if I wanted to. Maybe that would have been more natural. Multiplied by the volumetric flow rate. Let's call that VIA. Oh, it's maybe stupid notation anyway, but equals the flow rate and that is, oh well, okay, I've messed it up a little bit. I should have used AI here. So let me and not BI. That, of course, is this expression here, or this quantity. Multiplied by R, multiplied by, and then we need to use the temperature of the tank that is sending it, the one corresponding to the inlet pressure, the temperature related to this pressure. Like that, and then we have a similar one for inlet of for B. So we have PI2 V dot. Like that. And let's see. What should we do for this one? We could at least do P, let's see, we could use the pressure in the tank multiplied by the effluent volumetric flow rate equals total effluent volumetric flow rate, or T. That should work. And then we need expressions. We need to use these expressions for the volumetric flow rates. So we have V dot AI like that. Like that. Okay, and then we need to define these pressure differences, which should be quite straightforward. Let's see. So we have what did I call that? I called PI1, I guess. minus P and then okay, P minus ambient pressure. And then there is what is missing now. There is only one thing missing. We need these two. I have only the total of them. Right? I have only an expression for the total effluent flow rate. Right? So I need to split them up into individual species. So how do I do that? Any idea? Oops. Like that. It must be equal to the molar fraction multiplied by the total flow rate. And of course here I have used that this one. Okay, think a little bit about it. If I know when the class finishes and you rush out, if the number of people with glasses and people without glasses have been perfectly mixed before you rush out, and if I know the total flow out, the number of people with glasses will be the fraction of people with glasses multiplied by the total flow rate. And the number of people with, or the flow rate of people without glasses will be the fraction of people without glasses multiplied by the total flow rate. So it's the same thing. So we have quite a few equations here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 equations. 2 of them are differential equations. Did I say 17? So then 15 are algebraic equations. And this is a relatively simple system. So this is the DAE formulation. Suppose now I want to rewrite it into ODE form. How many equations will I then get? 2 differential equations. Same as the number of balance equations. And I will have only one output. The P, what was it? PA? Yeah. PA. Okay, so you, of course, if you reduce it to ODE form, you get much fewer equations. But they may be complicated. So typically ODEs, if you have fewer equations, it's sometimes a lot of work to reduce them to ODEs, and the result is normally could be quite complicated. If we instead use the DAE formulation, you have relatively many equations, and but they are in general simple, and very little manipulation involved in it. So typically to formulate DAs is less work because you avoid the manipulation. And to do the manipulation, you need to form these first anyway, typically. What about solution then? Well, of course, you could have a suspicion that it's easy or faster to solve few equations than many, which sounds reasonable. And that's probably true. You may get faster code if you first reduce it to ODEs. So the solution may be found faster. But then on the other hand, if you spend a lot of time on manipulating it, which is kind of an error-prone process, you easily introduce errors. Maybe it's better to formulate it as DAs and let the solver convert it to ODs or whatever they convert it to. So anyway, there are advantages and disadvantages to both. Suppose now that we suddenly decide, okay, we have spent a lot of energy on converting it to ODEs, and then we suddenly decide, oh, well, maybe we want a different expression for the flow rate. Then we have to redo it. But if we use DA formulation in Modelica, for example, we just have to change one equation maybe. So, I should comment on one thing. I should probably also have commented on that in the previous example with a single species. And that is, observe that I have in the flow rate out here, I say that the pressure in the tank is equal to, well, pressure P. What happens if the pressure in one of these tanks suddenly drop substantially so that it drops below the pressure in this tank? What will then happen? Then the flow direction changes, and then our model doesn't work anymore. Because this definition of the pressure difference assumes that the pressure at the inlet is higher. If it suddenly becomes lower, this is actually a flow out of the system. So we have to change sign. And also if we do the simulation and this happens, we get a problem because suddenly we take the square root of a negative number. So maybe if you want to make a sort of production quality simulator, maybe you want to think about that possibility and build the model so that it allows for change of direction. In that case, you have to think a little bit more. That's one complicating factor typically with gas systems, much less with liquid. So gas systems, or in more general systems where the density can vary, then you get problems like this. You could also have it in, for example, hydropower systems where you have a very steep so-called pressure shaft or penstock. Typically, at least in Norway, if you have typically a power system looks like this. You have a big dam, and then you have a transport pipe that can go for kilometers. And maybe the last few 100 meters or kilometer or something, there is a very steep drop down to the turbine. Okay? And this is called the pressure shaft or the penstock. And that can vary from I don't know, the highest drop in Norway is, I don't know, more than 1,000 meters. And the highest in the world, I don't know, but could be in, I don't know, Nepal or Peru or something. Countries with very high mountains, and it could probably be, I don't know, 1,000, 2,000 meters or maybe more, I don't know. So in this case, if you do some variation in the turbine opening, you can easily understand that you can actually get compression of water and very high pressures. So in that case, that's one example where you even for liquids may need to, when you describe the model, you may need to take into account that the flow direction may change, and then everything becomes more complicated. Of course, it's much more common in gas systems if you have a gas pipeline or something, or even a simple system like this. So I did it in this simple way just to not spend too much time on the model development. So let's continue with the chemical reactions. We have time for that. I'm sure you're not tired. You're fresh and feel like going into a new topic at the end of the Friday afternoon. So let's do that. Let's see, chemical reactions, reaction rates, and generation term. Okay. So since you have such a wide background, I cannot go into too much details about chemistry and so on, so we will try to do it in a systematic way. Important concept is stoichiometric reactions. And let's say we have, well, I take this example just because it's well known and I know it. I don't know fancy reactions. So. This is a reaction scheme for hydrogen and oxygen reacting to water. This equation here, or this reaction, is not stoichiometric. And why is that so? Well, some of you know it, of course. The reason is that to be called a stoichiometric reaction, the number of elements on each side must be equal. So if you see here, we have 2 hydrogen atoms here. We have 2 hydrogen atoms here. That's fine. We have 2 oxygen atoms here, but we have only 1 here, and that is not fine. Because of that, it's not stoichiometric. So how do we make it stoichiometric? We simply multiply each term with some number. And we can do trial and error maybe, and typically they should be integers, or they should be, not typically, but always integers, I think. But maybe at least rational numbers, not real numbers. And maybe the idea is to pick numbers that are as small as possible, so that this balances. And of course, if you remember from my example, I use this 2 times 1 times and 2 here. And if you compute it now, you see that you have 4 hydrogen atoms here. You have 4 hydrogen atoms here. You have 2 oxygen atoms here, and you have 2 oxygen atoms here. So this is stoichiometric. Each element has the same number of atoms on each side. This is kind of my abbreviation of number of. So this is stoichiometric, and then I postulate that it's not a postulation, but stoichiometric reactions can be written as like this. Some number nu1, this symbol is a Greek lowercase n. nu1 multiplied by s1 plus nu1 multiplied by, no, nu2 multiplied by s2, etc. plus nu_ns, number of species, multiplied by s, and s is the species. And of course, if you compare this to this equation here, you see you have 2H2 plus O2 minus 2H2O, like this. In this case, we have the number of species is 3, H2O2 and H2O, and these numbers mu1, mu2, etc. is 2, 1, and minus 2. Okay? This is not difficult. This is just a sort of a formalism. We can write it like this. Okay. And now we need to use a little bit of linear algebra, matrix multiplication, and that's not difficult either. We can also write it like this, where we infer matrix multiplication between the row matrix, this one, and this column vector of species. Or in the more general case, we could multiply nu1 multiplied by nu2, no, nu1, nu2, etc. to nu_ns multiplied by S1, S2 down to like this. So any stoichiometric reaction can be written like this. And then we simplify things and say that we call this nu, and we call this S, and then we can write it as like this. So any stoichiometric reaction can be written like this. There is no mystery here. The only thing you need to remember is that this is a row vector of coefficients, and this is a column vector of species, and we use matrix multiplication, standard matrix multiplication from linear algebra. Okay? What if we have more than one reaction? We can do the same thing, and then we can stack these coefficients. We have the same species, and we just stack this up into a matrix. So that we have one row for each reaction. Okay? So then nu becomes a matrix. And nu is known as the stoichiometric matrix. And I say here nu is some element of r to the power of nr times ns. And then, of course, you need to know what that means. Well, what I'm saying is that the elements of the stoichiometric matrix are real numbers. That's what the r means. And this means that there are nr rows. So we have the number of reactions. And we have ns columns, which is the number of species. So we have one column for each species. Okay? Now this is, what I said is that this coefficients nu should be integers, or at least rational numbers. So I should perhaps have used, I don't know, natural numbers or maybe q. Is that what you use for rational numbers? I seem to recall it's q. And maybe it's because it's sort of quotient or something, quotient of integers. So rational numbers are integer divided by integer. So I mean, they are not normally not real. I'm sure they are not real numbers, but that in that case it would be kind of a fake reaction. So anyway, so we can write reactions like this, and this is one of the few things in reaction engineering, or this part you need to know, that you can write it like this, and you need to know this. And one reason is that the rest that follows is much less chance of doing mistakes if you understand this. So let's it's getting cold. So we have a stoichiometric reaction. And we have, should I use R or should I use Q? Q? I mean, they are not real numbers. They are, okay. S is, of course, the species vector. NR is, so we have NR reactions. And for each reaction, we have a reaction rate. Okay? And those of you who have studied chemical engineering, and maybe you have had a course in reaction engineering, chemical reaction engineering, or something like that, then you have learned how to formulate expressions for this, or at least you have seen some expressions for these. Okay? For the rest of you, don't worry. If I give this in an exam, I will tell you what is the reaction rate. I will tell you that it's, for example, something like that. Don't worry about that. You're not supposed to know that. I will give it to you. But you have, what you are supposed to know is how do you use it. So we have NR reaction rates, one for each reaction, one for each row in this stoichiometric matrix. Okay? So now the big question is, how do we go from these reaction rates to the generation terms? How do we map from the reaction rates for the NR reactions to the generation terms for the NS species? Of course, these can be different numbers. There is a different number of reactions from the number of species. So how do you do this? And it's very simple. If we have a perfectly mixed volume, in other words, if you see this symbol of this impeller, we have this very simple relationship. The vector of generation terms, molar generation terms, and then of course you need to know what that is. But this vector is equal to the volume of the system multiplied by the transpose of the stoichiometric matrix multiplied by the vector of reaction rates. And then, of course, you need to know what does this mean. What is the vector of reaction rate? How do we formulate the vector of reaction rates? And how do we formulate this vector of molar generation terms? Look here, you see we have NR of these, right? And they look like this. It's a column vector of the reaction rates. And for the molar generation terms, we see that we have NS, just as many as we have species, which is a different number. maybe it's difficult to read, but it says the molar generation of species S1, the molar generation rate of species S2, etc., all the way down to molar reaction rate of, or molar generation rate of species SNS, and NS is the number of species. So this is what it means. This is a column vector. Volume is a scalar, a number. Stoichiometric matrix is a, or this is a transpose of the stoichiometric matrix. And this is the number of reaction rates. If you remember a little bit of linear algebra and matrix multiplication, you know that, as you see over there, the new matrix is nr times ns, and when we transpose it, it reverses the order, so it's ns times nr. ns times nr, and that is required so that we can multiply this vector with that matrix and get an n vector with ns elements. Okay, final warning, and this is very important. When we formulate the stoichiometric matrix here, we have specified a certain order of the species, right? Of course, if I had changed the order of hydrogen and oxygen, I would also have to change the order of these. So, point is, when I have set up the stoichiometric matrix, I have used a certain order of species. And I have to use the same order here. If I don't do that, I'm messing things up completely. So when you have defined the order of species, you have to use that everywhere. Okay? Second thing, if I have several stoichiometric reactions, so I have several rows here, I have to make sure that I use the same order of the reaction rates here that I used here. So reaction rate number 1 has to correspond to the first row in the stoichiometric matrix. And reaction rate number 2 has to correspond to the second reaction rate, the second reaction, and so on. So remember, when I talk about vectors, that has a very important consequence. A vector is simply a list of numbers, but the order is fixed. When I have defined the vector, you cannot go back and change it without changing everything. So remember that when we talk about that something is a vector, the order is fixed. So this is actually very elegant. When I took reaction engineering courses, we didn't learn this. And it was always a nightmare to figure out how to actually set up this. You really had to think, set things straight in your head when you computed how much, for example, if you have a reaction rate of water, in this case here, what number do you multiply that reaction rate to get the generation term for oxygen, hydrogen, and water, for example? That you do automatically when you do it like this. You don't even have to think. Okay? We have actually 2 minutes left, so there is no time to do an example. But I recommend that you look into one of the examples. There are several examples with reactions, so look at that. And then next week we are going to talk about momentum balance. Momentum balance will probably have some importance in the project, which will be about a hydropower system. Alternatively, it's possible to use mechanical energy balance.